Okay. Okay, thanks, Miguel, and thanks to the organizer for keeping up with this very nice seminar series. I really enjoyed following it throughout the last year. So I will talk today about a paper we put out about a month ago together with Severin Lust, Common Waffer, and Kai Xu, which has the same title as my talk, Holography and the KKLT scenario. So let me give some introduction. Let me set up a little bit the stage. So I think we can agree that at large scales, observations suggest that our universe seems to be homogeneous and with a small but positive cosmological constant, which at least seems to be constant over a long time. So the late-time universe in which we're living should be describable by a quasi-de Sitter geometry. And so it is I think for theoretical physics in general, it's a very important task to look for models or for theories that can actually accommodate such quasi-de Sitter geometry and look for vacua with positive cosmological constant. I think for those who attended yesterday's swampland seminar, the poll suggested that this is also one of the important problems we have in the swampland problem or in Strigfino that we should address in the next years. The problem, however, as was suggested also conjecturally in this paper, is that quasi-de Sitter solutions are very difficult to obtain in consistent theory of gravity. Of course, one can write down such a potential here just in effective field theory, just by coming up with some potential, but embedding this in a consistent theory of gravity seems to be very difficult. And for instance, weakly coupled string theory, which I think is currently our best shot at a consistent theory of gravity, has the problem that we always get runaway potential, which with a slope that is too big to realize quasi-de Sitter space, such that at weakly coupled string theory, we cannot really realize such a de Sitter vacuum. So if a quasi-de Sitter solution exists in string theory, there should be somewhere interior of the field space, where unfortunately we have limited control over the theory. This is the famous Stein-Seibert problem. So either the non-perturbative regime gives us, the perturbative regime always gives us the runaway. And so if we want to look for the de Sitter vacuum, they should somehow hide in the strongly coupled regime. However, one could try to find de Sitter vacuum, which are not at strictly coupling, where these arguments about the asymptotic runaway direction implies, but still in a controllable regime by taking into account some non-perturbative corrections, which I think is the idea of these very celebrated works. So in some sense, one would like to look, one would look in some intermediate regime where we're not at strictly weak coupling, but also don't lose full control over the EFT. So the proposals for this typically consist of a multi-step scenario. One typically tries first to find either a supersymmetric or non-supersymmetric, but some kind of ADS vacuum, and then uplift the vacuum energies to small supersymmetry breaking effects, such as anti-D3 branes. This is illustrated here. In this work, we exclusively considered the KKLT scenario, called after Kachu, Kaloshin, and Trivedi. And in this scenario, the first step aims to find a supersymmetric ADS vacuum with small cosmological constant, which can then be used subsequently to uplift through an anti-D3 brane in a very warped part of the geometry to a de Sitter vacuum. And this aims to achieve this in type 2B or F3 or flux compactifications, taking into account non-perturbative corrections. And what we asked in this paper is, can the first step of KKLT, without talking about anti-D3 brane uplift, but just the question, can we get a supersymmetric ADS vacuum? Can this be achieved in a type 2B F0 flux compactification in such a way that the resulting supersymmetric ADS vacuum has a small cosmological constant, and B is still somehow in the regime where we have control over the EFT. So this will be the outline. I will briefly review the first step of the KKLT scenario, because this is the only thing I will talk about here. And then I will talk about the conventional holographic dual of this SUSY ADS vacuum. Then we'll talk about how one can give a bound on the CFD central charge, which should map via holography to the value of the ADS cosmological constant. And then put everything together and argue for holographic obstruction from this perspective for the first step of the KKLT scenario. Okay, let me just start with a very brief review. KKLT. So we consider type 2b on a Calabi-Yau orientifold, or F theory on an elliptically fibered Calabi-Yau fourfold. And we turn on RR or NS three-form fluxes, F3 or H3 or an F3 or KCT four-form flux that satisfy the Tapper cancellation, which essentially means that the curvature induced by that induced the three-brane Tapper induced by orientifold planes is cancelled either by the three branes or by the flux. We will be mostly interested in the case where we don't have additional D3 branes, but we cancel the Tapper purely through the flux. Then we get a scalar potential, essentially from the fluxes and from non-perturbative corrections, which is, I think, well known at this point. And here we have essentially the superpotential, which at leading order is given by the Gukov-Witten superpotential that is essentially induced by the fluxes that we turn on in our internal geometry. And since the ADS vacuum required for KKLT-like scenarios should be supersymmetric, we should solve the supersymmetry equation, i.e. the F-term equations, which is just that the scalar covariant derivative of the superpotential vanishes. So if we just had the Gukov-Witten superpotential, the only solution to the F-term equations would be in the decompactification limit for the Calabi-Yau, essentially because the superpotential, the Gukov-Witten superpotential as such does not depend on the Kähler moduli, and then dAW equals 0 can only be solved asymptotically in the decompactification limit. To get a supersymmetric solution away from the decompactification limit, this is what essentially is at the core of the KKLT scenario. We need to include, or we need to take into account, the non-perturbative corrections, essentially through instantons or gauge condensate, which give an extra contribution to the superpotential in terms of this instanton sums that explicitly depend on the Kähler moduli, but also through can in principle through this Pfaffian determinant on the complex structure moduli and the fluxes. So to have control over the instanton expansion while still solving the F-term equation, essentially it turns out that these both terms, the classical plus the instanton term, need to both be of the same order and both exponentially small. And essentially, since we want to have this exponential suppression factor to have the instanton expansion under control. Then the potential at the minimum, if you just plug this in, the F-term equation, the F-term condition is just given essentially by the value of the superpotential square times the scalar factor. And this needs to be, of course, exponentially small if W is exponentially small. So one insight one can get is by looking essentially at this quantity. So as I said, the scalar potential at the minimum essentially depends on the scalar potential times superpotential, or this combination is essentially the one that appears. In terms of this superpotential, the covariant, the F-term equations essentially reduce to just the normal derivative, not the scalar covariant derivative of this Z, curly Z, to vanish. And then the cosmological constant is essentially just given by a factor times mod Z squared. So this equation is very reminiscent of an attractor equation for black holes, as was already noticed very briefly after the KKLT paper came out. And this is essentially what motivates us to study also the holographic dual. But let me just briefly recall what do I mean with the attractor equations for a black hole. Take, for instance, 1/2 BPS black holes and type 2b Calabi-Yau compactifications. These can be obtained from D3 branes on special Lagrangian 3 cycles in the Calabi-Yau threefold. And here we can define a similar quantity, which I now here called normal Z, not curly, which is essentially the period of the holomorphic 3,0 form over the circle. I think there's a square root here missing, normalized properly. And then this can be identified with the mass of the black hole, and the back direction of the black hole is in such a way that actually we reach the attractor point where precisely we minimize the central charge of the black hole, and the modular at the horizon of the black hole with near horizon geometry ADS2 times S2 are precisely fixed to this attractor value of this black hole. And then we can identify this critical value of Z with the mass of the black hole, and we can calculate the entropy. And we can do the Strominger-Waffer theory for this attracted for this BPS black hole. But importantly, we need a BPS. We need a D3 brane on this BPS special Lagrangian of the supersymmetric special Lagrangian cycle to get a solution essentially to the attractor equation dz equal to 0. So similar to that, we proposed what we would call the conventional holographic dual of the SUSY ADS vacuum. So what are the insights? Similar to the D3 brane black hole example that I just reviewed on the previous slide, one can dualize the F3 and H3 fluxes into branes, such that instead of the ADS vacuum, we look at the dual theory that is obtained in this case by NS5D5 branes wrapping the dual cycles. This was already suggested just after KKLT came off by Eva Silverstein. And now these branes are unlike the black hole in the D3 brane example, these are domain walls in 4D, so they have very low codimension, but these would be expected to be dual to the ADS4 vacuum. And since the KKLT requires a supersymmetric ADS vacuum, we would also expect the domain walls to be 1/2 BPS. So whenever we want to have a supersymmetric ADS vacuum, we would have to look at branes configuration that are also 1/2 BPS. This was also discussed in this paper 15 years, I think, ago. Actually, what we want to check is, or most of my talk, I won't talk directly about the KKLT type 2B F theory setup, but I want to go to the analog 3D M theory setup, because here the BPS conditions is easier to check, because essentially we just have geometry. We don't have to deal with NS5 plus D5 branes, but essentially NS5 and D5 branes unify in a single object M5 branes. And so we consider M theory on Calabi-Yau 4 folds with G4 flux, which will be dual to M5 branes on certain cycles. And we want to find KKLT like ADS3 vacuum in this case. So all these arguments about the statistical arguments that there should be enough flux, or that the possible allowed flux shell is big enough such to find some vacuum with small cosmological constant should equally well apply to this KKLT like vacuum in ADS3, and also in the end, these M5 brane and these NS5D5 brane systems are very much related. So dualizing, as I said, the G4 flux in this M theory setup, wrapped on 4 cycles in Calabi-Yau 4 fold, we get M5 branes wrapping 4 cycles in the Calabi-Yau 4 fold, which are now string or domain walls in 3D. The 1/2 BPS condition, which we require for such in order to have a dual supersymmetric ADS, requires that these 4 cycles L4 should be calibrated in order to preserve some supersymmetry. And then this curly Z that I defined previously, which is essentially the e to the k times the modulus of the superpotential, can be interpreted as the tension of a domain wall in 3D, including all non-perturbative corrections. So really, this domain wall in the full theory will be sensitive not just to the Gukov-Witten superpotential, but to the full superpotential, including all corrections. The supersymmetry essentially then tells us that this calibration of L4 is equivalent to the fact that the F-term equation, which is just, as I said, just in terms of the Z, reduces to the ordinary partial derivative of Z to vanish, that this has a solution. So we are interested in primitive G4 fluxes, because these are the ones that in the end we can uplift to F theory. So the Kähler form wedge our G4 flux should be 0. This means that L4 has to be, so the dual cycle to the Calabi-Yau 4 fold has to be a special Lagrangian, which is essentially the statement that the that the Kähler form J4, which is the same as J, vanishes if restricted to L4, and that essentially we have a constant phase for our omega 4 or photomorphic 4. So unlike the D3 brane example that I mentioned for the black hole, which just depended on the complex structure, the tension of the domain wall already at the perturbative level depends on all the moduli of the theory, because essentially the prefactor e to the k over half contains both the Kähler potential of the complex structure sector and of the quantum Kähler moduli space. It's essentially a consequence of the fact that in an n equal 1 or an n equal 2 d equal 3 theory, the modular space does not factorize anymore. So we have this the extension of the domain wall, which we want essentially to extremize to find our supersymmetric ADS vacuum. Notice that this special Lagrangian condition is a much stronger condition than one would usually assume with flux compactification, which would be just a self-duality condition on G4. But here we really say, okay, the full theory, if we take into account all non-perturbative corrections, if we want to have a non-trivial ADS vacuum, should correspond to an M5 brane on a special Lagrangian cycle. So the M5 brane of these Slack cycles generate the ADS vacuum. With what I mean, essentially, we have a domain wall. To the left, we either have just space-time filling M2 branes or nothing. And then to the right, asymptotically, we would asymptote to the supersymmetric ADS vacuum. These are essentially the BPS conditions that were already written down in 92 by Svetic et al. Essentially, we have this flow, which is governed by this curly Z, so essentially by the tension or the central charge of the M5 brane. And asymptotically far away, if we have a supersymmetric ADS vacuum, which means this vanishes, essentially what we get is then a constant warp factor here, which then asymptotes to an ADS3 vacuum. Unlike in higher codimension examples, for instance, the accuracy, like the black hole example, the ADS3 here is realized asymptotically far away from the domain wall, such that we should look at the IR of the world volume theory on the domain wall, which we expect to be dual to the supersymmetric ADS3 background that we wanted to get from this KKLT like M theory construction. So essentially, M5 domain wall generates this ADS vacuum, and the world volume theory should flow in the IR to the theory dual to this ADS background. So the world volume theory of the M5 brane on a Slack cycle has n equal 1,1 in 2 dimensions, which from a holographic point of view is a good news because we want a supersymmetric ADS, so the dual theory should also preserve half of the supersymmetries. In the UV, it is in general not a CFT, but it can flow to 1 in the IR, which is precisely the case that we're interested, that we in the IR have an ADS geometry, whereas close to the domain wall, this does not necessarily need to be the case. By the C theorem, the UV and IR central charges satisfy that the UV central charge or the degrees of freedom essentially are bigger than the IR central charge. So we can give a bound on the IR central charge, which is what we are in the end after, because this will be the dual theory, to the UV central charge. By the duality, holographic duality, the central charge and the ADS radius are expected to be related to each other, such that if we give a bound on the central charge, we can give a bound on the ADS radius. So the task is now to estimate the growth of the UV central charge, because this gives a bound on the IR central charge, which then is proportional to the ADS radius for the world volume theory from M5 brane on a Slack 4 cycle. The question more precisely is, for cycles that are compatible with the Tadpole cancellation, so in principle we cannot take arbitrarily big cycles, how can the central charge be exponentially large, which would mean that we can get exponentially large ADS vacua from these kind of branes. So let me
Sorry,
argue.
Max, can I ask a question?
Yes.
Sorry for interrupting, but it feels to me that something very important happened exactly at this step. So, I mean, you will count degrees of freedom in the ultraviolet, and you also then assume that the instantons, the non-perturbative corrections required to get the ADS are not important in this counting, because you're only looking at the M5 on the Slack, which is just, turning fluxes into branes. So do you agree with me? But this is actually a highly non-trivial step that you can say, I forget about, the analog of the gauge condensate, which is crucial for KKLT, but at this point you say, I ignore it. And the counting is only, counting due to fluxes becoming branes. Is that my correct interpretation? Or
this is correct. We just count the flux, the degrees of freedom on the branes, because in the end we expect whatever. So the trivial solution or this trivially, one would say, okay, the central charge is minimized at infinity at the decompactification. We now say, okay, there could be in principle the possibility through non-perturbative effects that correct the central charge correct the Z that I introduced, that there is another non-trivial extremum of essentially mod Z. And we're saying, okay, but what we're counting are the degrees of freedom in the UV of the M5 brane, which is just a topological. This is just a topological counting, because essentially we look at the deformation.
Sure, but is it obvious that in the UV these instantons don't play a role? Is that an obvious statement?
So we look at in the UV, these don't play a role, and then we might flow towards the interior of the modular space. But the idea of KKLT is that you're still somehow in the large volume phase. So there's no phase transition happening. There's nothing. So essentially, our geometry of the special Lagrangian cycle might get changed a little bit, but the counting of the degrees of freedom should still be correct. Even though we don't know what actually happens if we flow to the IR, because we just say, okay, we count the UV degrees of freedom, which we can count through the deformation space of our special Lagrangian cycles, and then we say this should not, since we still want to stabilize at roughly large volume, these topological quantities that we count, this should not change slightly in towards the interior of the modular space. So because essentially the M5 brane feels all the instanton corrections, and if we look at the UV degrees of freedom, this should still be the correct counting that we do.
Sorry, I have a much more elementary question at this point. I mean, how do we know about the duality at all? So the branes are the boundary of the ADS. I mean, you need to go over the domain wall to get to ADS, but you are claiming that the branes are the dual CFT to the ADS. I think it's not obvious.
So what we're doing is that what we're saying is what we call conventional holography, which is essentially what you always do in string theory. You have a flux. Also, if you look at the D3 brane example, you have a 5-form flux on the sphere times the cycle in the color we of 3, and you can look at the dual theory by just dualizing this flux essentially into a brane, which is in this case the D3 brane. And here we're saying the same happens, because these are all the examples we have in string theory. The same should happen for the KKLT scenario. So we say we take a conventional approach to holography, saying, okay, we just get the CFT by dualizing the flux in the background, the flux that we turn on along the color via 4-foot. In this case,
I wouldn't agree that this is obvious. Sorry, I mean, maybe I'm too stupid. I discussed with several colleagues. I mean, there's a very sharp statement that the theory that if you have a transition from Minkowski to, or approximate Minkowski to ADS through going over the domain wall, that this domain wall contains the CFT dual to the ADS. I just don't see why this is the case. This is not how normal ADS CFT on the ADS 5 times S5 works. I mean, I'm sorry.
I agree that this doesn't work. So it is different from the normal ADS 5 times S5, because here we're dealing with a very low codimension system, because essentially this is the problem KKLT, or the problem we are facing. Precisely. We have a very low codimension system. So we don't essentially have this transfer space, which is essentially the S5 for D3 brane that becomes an S5, or in the ADS 2 times S2 case of the black hole. But so here we have essentially a codimension 1 object, but we apply the same philosophy that we always do in string theory, dualizing the theory, and then instead of flowing in the near horizon geometry of the black hole example, or the D3 brane example to the ADS, what we have here is, since due to this low codimension, we essentially have this domain wall with asymptotically far away flows to the ADS background. But we still say that this is the correct holographic interpretation, because this is how we always do it in string theory.
I don't understand. The word always, I mean, sorry, I mean, it's a key point, right? I mean, you're destroying KKLT, 100% completely killed. I mean, you need to make this point more sharp to convince me.
But wait, there's a confusion related to my question. They are not saying this is the CFT dual to KKLT.
Yes.
No, they're not saying that. This is a QFT in the ultraviolet, where they're counting the degrees of freedom, and then it flows in the infrared to the CFT, which nobody knows. And so they count the degrees of freedom in the UV, but that's not a CFT, that's a runaway, that's a QFT.
No, but they are saying that, whatever it flows to the infrared is a CFT, and that CFT is the dual of KKLT.
Yes,
that's what they're saying.
But we're not saying that it's the UV theory on the brain. We're just saying that from this holograph, from this point of view, where we have the domain wall that flows in the infrared. So we just replace, as one would do it in the ADS 5x5 example, one would replace the flux by these 3 branes. We're saying now in the infrared, this is the theory essentially. This domain wall is the defect that gives rise to the ADS in the infrared or asymptotically far away from our domain wall.
Yeah, exactly. But in the ADS5 case, you can go away from the brain stack, and you see there's a localized brain stack, and the physics that is there must be the same that you see in the ADS and the same that you see in the brain. But here, you approach the domain wall from one side, and there's something on the other side, and you are claiming that this other side is completely captured by the wall. It's just not obvious to me. I'm sorry.
Sorry, Arthur, sorry to interrupt. I think this is a very interesting discussion, but maybe we can keep it for the end of the talk. I think we presented the point already, and so we can perhaps wait for further discussion until the end of the talk. Thanks.
Okay, so let's come back to that point. For now, I want to present how. So in this holographic setup, or in this setup where we say our domain wall, the theory on the world volume of the domain wall flows in the infrared to the dual theory of the ADS vacuum. We now say, okay, we want to bound the CFT central charge in the UV. So we want to find a parametric growth of the UV central charge for the world volume theory of an M5 brane on a select 4 cycle. So with parametric growth, I want to understand how does the central charge behave under essentially a rescaling if we make the cycle bigger and bigger. So we're interested, so to say, in the large in the large n limits, but still compatible with the tadpole conjecture. To do this, let's consider related cases where we also have ADS3 geometries sometimes in other compact space, which are, for instance, the MSW strings, M5 on holomorphic C4, which have a near horizon geometry, which is ADS3 times S2 times Calabi-3, which has a world volume theory on this M5 brane with n equals 0,4 and d equal 2, or M5 brane on holomorphic curves in C4 in a Calabi-4 fold, which should then also give rise to an ADS3 times Calabi-4, but in this case we have n equals 0,2 supersymmetry on the domain wall in this case, and the last case, the case 3, is which we are interested in. So take, for instance, the MSW string. There one can calculate the central charge using anomaly inflow essentially on the effective string, and one sees that that essentially the dominating term in the case that we want to rescale C4 to n times C4 grows cubic in n, essentially because of the first term in CL and CR. The other ones are subleading. So here we see that the central charge grows like n cubed of when under rescaling C4 going to n times C4. In the second case, M5 brane on holomorphic, one can again use anomaly inflow, but here instead of a term that is proportional to C4 cubed, we have a term that is proportional to C4 squared. So here we see that the central charge on the world sheet essentially of this M5 brane on this effective string in 3D scales like n squared under rescaling of our curves of the holomorphic curve. So we have two different scalings, but we already saw that in the case that is more similar to our case, which is the case of an M5 brane on a holomorphic curve. We have an n squared scaling. So what are now the degrees of freedom for our case that we have an M5 brane on a select 4 cycle? So first, just by reduction of the M5 brane action, we get B2 plus right moving and B2 minus left moving scalars. In addition to, of course, the scalars coming from the tangent space of L4, from the modular space of deformation space of L4 as a select cycle, which essentially, due to the property that the normal bundle of a select cycle is equal to the cotangent bundle, tells us that the dimension of this modular space is just B1 of this L4, so the first Betti number, which tells us that we have B1 left and right moving scalars coming from the deformations. So that this gives us then the number of degrees of freedom on this brane, and also a way to calculate the central charge, which essentially one can write as a factor coming from the B1, so from the deformation of the special Lagrangian cycle, and the Euler characteristic of L4. Now, the Euler characteristic for a slack cycle, essentially because of this property, is just the self-intersection of L4, such that we see that the UV central charge is essentially proportional to L4 plus a term that comes from B1. So we expect that CUV should grow then like n squared, especially if we rescale L4 to n times L4, which essentially means that if we take n copy, if we have n L4, then separate n copies of it, it should intersect precisely at L4 points, which should give a universal contribution to the central charge. Also, B1 should not grow faster than some universal constant times L4 times L4, which one can actually support by in the orientifold limit, which we have then lift to type 2b through black hole arguments. For details, see our paper. So from the RG flow, we know that the IR central charge will be lower than the UV central charge, which then should just scale like some constant beta order 1, order 10 perhaps times the Euler characteristic, i.e. the self-intersection of this slack 4 cycle. However, we need to satisfy the tadpole cancellation, which is essentially a condition that the Euler characteristic of the fourfold should be equal to the number of the 3 branes times the self-intersection, or 1/2 the self-intersection of L4. We are interested in the case where essentially we have the highest statistical probability to find low vacua with small cosmological constants. So we want to have large fluxes or large fluxes with large contribution to the tadpole, such that we say, for instance, for simplicity, we set this in D3 to 0. So the central charge of the M5 brane on the slack 4 cycle is thus essentially bounded by the tadpole cancellation condition. So now I translate this into a holographic abstraction to KKLT. So the UV central charge, as I said, is parametrically bounded by a factor times the Euler characteristic. My internet, okay. By central charge, and the ADS radius are then related essentially through proportional to that up to some power, which depends on the dimension of the ADS space, whether we consider the 3-dimensional case or the 4-dimensional case. For ADS3 vacua, we hence find that just the ADS scale will be lower equal to than the Euler characteristic of the fourfold. So the largest known Euler characteristic for a fourfold is essentially around 2 million. It has been investigated in these 2 papers, such that LADS can be of the order of 10 to the 5. That's all, which sounds good because this is already quite big. For orientifolds, we can make a similar estimate of the central charge for the D5 and NS5 brane system, which should be just proportional to the M5. And there, the Euler characteristic is bounded essentially by just looking at the fixed point theorems by 252. So we can get ADS radii, which are of order of 20. So in the F theory case, one could say, okay, maybe we can really get huge, relatively large ADS. However, the question is still, are these ADS vacua indeed weakly coupled as in the KKLT scenario? And therefore, we consider the species scale, which is essentially the scale at which gravity becomes strongly coupled in the presence of n-like particle species, which again depends on the precise relation depends on the number of dimensions. For Calabi-Yau compactification, the number of light species, even if we stabilize them, but as long as we stabilize them below the string scale, as we would always do, is given essentially by the number of moduli, which for the fourfold would be just H11 plus H31. So now recall that the Euler characteristic essentially is also proportional to these 2 quantities, such that we know that parametrically, the number of light species exactly is also bounded, in this case from below, by, or roughly, by the Euler characteristic of the fourfold, such that we know that the species scale will also scale with the, for instance, in this 3D case, with the Euler characteristic of the fourfold. And we can then compare the species scale and the ADS scale here in the 3D case. And we see that they essentially are both bounded, one from above, one from below, by the Euler characteristic of the fourfold. So the ADS scale is at best at or below the species scale. So any ADS vacuum that we would get would be necessarily in a strongly coupled regime of theory. And so we cannot even trust the vacuum with small lambda. The same also works in 4D because the species scale and the ADS have the same dimension dependence. So from this conventional holographic perspective, where we identify the dual theory as the dual theory living on the domain wall of from the M5 brane, KKLT like SUSY ADS vacuum cannot be realized. So let me give my conclusion. So we considered the first step of the KKLT scenario from a holographic perspective. So we wanted to see, can we get supersymmetric ADS vacuum from flux compactification? And we used what we call conventional holography by just dualizing the flux through 5 branes, which is actually something that was already proposed very early on, just dualizing 5 branes. We took here a slightly different perspective because we considered directly M5 brane, not D5 NS5 brane. The supersymmetry equations can then be identified as an attractor equations. And this tells us that essentially the supersymmetric vacuum requires supersymmetric branes, which also makes sense from this conventional holographic perspective. For simplicity, we took M theory analog of KKLT, where we said that supersymmetric vacuum are dual to branes on Slack cycles. And in the infrared of the theory, we should get a theory that is dual to the SUSY ADS. So the UV central charge, which then bounds the IR central charge, is bounded essentially by the Euler characteristic of the fourfold, which gives a cosmological constant that is bound by the M2D3 brane tadpole, which we then said is also the same thing that sets the species scale such that the ADS scale is always above or at the same order as the species scale. Thank you very much.
Okay, Max, thanks a lot for the very nice talk. We are a bit of a time, so is there time for a couple quick questions?
I just wanted to comment that I think my question was the same as Thomas's question. I didn't really understand Thomas's question well, so I think it's really the same question. Because the UV degrees of freedom, I mean, so Thomas asked about whether it's true that the UV theory is the same as the IR theory. I mean, whether the IR theory comes out by flowing. But really, my question would then be: is it clear that in the UV theory you can neglect the degrees of freedom which are in the ADS? I mean, all the fluctuations, long distance fluctuations in the ADS, they should, in my opinion, be part of the UV theory naively, if you interpret the brane to be all of the physics. And it's not clear that this happens. That's maybe a different way to phrase my concern about the duality holding. And I think it's the same that Thomas asked.
So we're not doing, in that sense, a UV holography, because as Thomas said, the UV theory is not necessarily a CFT. I mean, we say it flows to the CFT, and we say that the infrared theory, this should be the CFT. This should be the one that is dual to the ADS background, and we're saying that our counting, however, we don't know what this flow is, and especially there needs to be different flows because we need to have different critical points for our Z, because there's one trivial at infinity. We're saying that this counting of the UV's degrees of freedom is is just topological, so it does not really depend on the details of the flow. And the other argument is that this domain wall should really, because we take the full Z, including all non-perturbative corrections, should include the information somehow of the non-perturbative corrections. So to say differently, we don't expect, if you don't have a supersymmetric brane, we don't expect that the full superpotential, the extremisation of the full superpotential or the full Z should have a solution.
Okay, Dieter, I think you also have a question. Please just go ahead.
Yeah, it's not really a question, but I like also to comment on this domain wall flux correspondence, which in my opinion works very nicely, at least in the UV. I mean, Max was so kind to cite our paper from 07, and I can briefly recall what we did there. On the one hand, if you have these domain walls in the UV at least, they provide the attractor equation and they stabilize the scalar fields, and they basically give you the value of the ADS radius, at least on the one side of the domain wall. And if you compare this with the corresponding fluxes, you get precisely the same result. You get the same ADS vacuum, you get the same ADS radius, and you get the same values for the scalar fields in the vacuum. So this works perfectly. So I think this domain wall flux correspondence is very good and can be used here. Then of course there's a second step. I mean, this would give you then the bound on the, as far as I understand, this gives you the bound on the central chart in the UV. But so to say, if one can now safely assume the argument that the running to the IR has no discontinuities. Of course, certain things can happen like brane recombinations or other non-perturbative effects. But if the C theorem, so to say, still works, and if there are no big discontinuities, then I think the central result in the UV gives you still a good bound on the IR, and since the bound goes in the right direction, therefore I'm quite happy to accept this bound.
I completely didn't understand. I mean, it's a very important point. I completely don't understand. Sorry. I mean, now I'm really worried that you are convinced of this, and I just don't understand. Can you explain again why the brane theory, so the brane theory, the local brane theory, right, in the UV, is the UV theory of the whole half space? That's what you're saying.
Yes, I think that's true if I understand your question correctly, but I think that if this is what you're asking, we have a domain wall, and in the asymptotic far away, so to say, on the one side of the domain wall, we have this UV, so to say, ADS vacuum, and I think it's correctly described by the degrees of freedom of this domain wall, at least in the UV.
But how can the long distance fluctuations of the whole infinite ADS be encoded in the UV degrees of freedom of that domain wall? That's, to me, I just don't see an argument. I mean, you can say that, and I just don't see it. I need an argument for that.
Okay, I at least trust it because the domain wall attractor equations precisely lead to the same vacuum solution, and literally you can read it off as a flux vacuum, which in both cases is ADS4 or ADS3, depending on which dimension you are in. So this we have shown in the 07 paper, studying several brane configurations. Of course, we did not talk about bounds, and we did not talk about dual CFTs and these kind of things, but we were, so to say, analyzing in that paper the duality between the domain walls and the fluxes, and we found a perfect agreement there.
What do you mean by duality? Sorry, duality. I mean, of course, the domain wall encodes information about the fluxes and hence about the ADS. But what exactly?
The domain wall are basically the sources for the fluxes, right? In the conventional, old-fashioned picture, like also which is true for D3 branes and 5-form fluxes. I think Max was mentioning this for ADS5 times S5 in the same sense.
Yeah, but that's obvious. I mean, that's, of course, the fluxes. I mean, the brane source the fluxes, of course. I mean, I don't understand why do you use the word duality?
Maybe the duality is a big, too big word.
I mean, the entire duality. Sorry.
Yeah, sorry, Max. Say.
I mean, the duality in this case is very confusing because in the end, it also, as we show, it doesn't really work because we have this low codimension. But it is the same picture that one has in the MSW picture that I reviewed. And as Dieter said, essentially, if you make it in other configuration, as in their 07 paper, you get the attractor flows. You get that you need calibrated. You get that you need calibrated branes, and it is just what this low codimension, which makes this look very weird, because essentially, as I said, you don't have the additional compact space like the S2 or whatever, But this essentially is the statement that we would expect naively that the only the critical point for our solutions are the ones where we decompactify and have a trivial CFT, have a trivial theory. So because this is one attractor point for sure for our system of fluxes.
Okay, are there any further questions for Max? Well, enough. Thanks again for the nice talk. And see you guys next week for yet another round of string field seminars. Looking forward to it. Bye. Thanks for coming.
Thanks, Max. Bye.
Anybody still there? Anybody still? I mean, Miguel, can you convince